start to discuss today about membrane contactors. All the other operations that we have been discussing until now, the membranes utilized were characterized by some parameters as permeability, but also selectivity. So we defined the rejection coefficients, perm selectivity, or just selectivity, etc. When you are discussing about membrane contactors, we are not looking anymore to membrane with property of selectivity. The function of this system is just to optimize contact, the name contactors is for there, between different phases. Liquid, solid, liquid, liquid, gas, liquid, etc. And this kind of unit are today not so well present at industrial level as the one we have been discussing until now. Are all new membrane operation, which however are becoming more and more interesting day by day. First of all, because they are able to redesign basically most part of the unit operation of a process engineering in a way much more appropriate in the logic of process intensification strategy. The saying that all these operations are membrane operations, so by definition they are flexible, they have a very small footprint, relatively low energy consumption, and easy concept, that means easy to operate, remote control, automatization, all these different parameters which we define as a part of the process intensification strategy are present, and the equivalent operation in traditional process engineering are not consistent with all that requirement. Most part of the contactors that we will discuss, we operate in water system. However, keep in mind that everything we are discussing in this system and today are utilized basically in an aqueous solution can be transferred to non-aqueous solution. So in perspective, when this system, if they will successful as reverse osmosis, ultrafiltration and others, you can tomorrow have a situation in which this system is not an aqueous solution, is a solvents of different kind, and in this case we have to remember that some of the properties of the membrane that we are discussing will be totally different from the one we are discussing when we are looking to aqueous solution. For the moment, however, the system will be much more, will have much more opportunity than just the one that we are discussing today. This is an example of one of the most interesting membrane contactor today, which is what is called a membrane distillation. Membrane distillation is nothing more than distillation, nothing different. All the equations that you have been studying in your basic course in chemistry or in chemical engineering, all the equation familiar to you, Antoine equation or phase equilibrium that are familiar to you will be valid here. The engineering of this system is very different. In normal membrane distillation, you have evaporation, condensation, and different kind of configuration, plates, big column of thousands of different places where evaporation, condensation is taking place, etc. In membrane distillation, everything is the same except the phenomena of evaporation and condensation is taking place at the mouth of a microporous hydrophobic membranes. You evaporate on one side and you condense on the other side, exactly as in the place of a distillation column, but we are using billions of pores of the membrane that you are going to utilize, as, by the way, nature is using already. Your skin is a typical membranes of this kind, hydrophobic, microporous. Hydrophobic means, if we are discussing about water, that the liquid phase will not penetrate in the pore of your membranes. These materials to be strongly hydrophobic, such a way that no liquid will penetrate. If the liquids penetrate, the system does not work. So we can anticipate that the problem of fouling that we've been discussing when we have been talking about reverse osmosis ultrafiltration will be different in membrane distillation. Part of the traditional fouling basically is not very important, but new form of fouling can be present. For example, if for any reason the interaction between the component of the feed solution and the material forming your membranes will induce chemical transformation in the system, and this system will not be anymore hydrophobic, but becoming hydrophilic. This is a big fouling. Liquid will penetrate. The system does not work anymore. So we have to learn how to utilize material for this specific application. You will see that all the material that you are using in all different contactors today, we will discuss some of them, but basically distillation, membrane crystallization, membrane emulsification, membrane condenser, membrane dryers are just the one under study today. The one that we call membrane distillation is the most popular. Membrane distillation is already present at industrial level, not on large scale around the world, but many countries, pilot plant producing 100 cubic meter of water per day, relatively small to RO, are already running. And more research is in progress all around the world to make this system, and we will understand why, by the way, at the industrial level. One of these limits, one we have is just that the membranes available, very different from the one we saw in RO and FM ultrafiltration. Remember, big table with a lot of membranes, different company working. This is not the case here. People are now producing, and specifically, all the membranes we are using are not produced for membrane distillation. Are traditional membranes produced for microfiltration, ultrafiltration, adapted to work in this case. And that is one of the problems for much bigger utilization of the potentiality of this system. So let's talk a little bit about the most interesting and well-known process, membrane distillation. You have a microporous, strongly hydrophobic membranes. We will see which material we are going to use. In principle, characterize this kind of structure, irrealistic. You see, all the pores seem to be equal and parallel. That's an ideal figure. Unfortunately, we don't have this. And that is the problem. In principle, this kind of configuration is not only ideal, sometimes necessary, because you will learn that the size of this pore is one of the parameters that we have to control for realizing just the membrane distillation. If these pores are becoming too large, liquid will penetrate. Also having a hydrophobic material. And when you will study about membrane preparation today with traditional phase inversion, you will learn that it's not easy to have a very narrow pore size distribution as this one, all the pore equal. Normally you have a large pore size. When you say that membranes is 0 to 2 microns, that means most part of the pore are 0,2. But always you will have some pore 0,5, 1, 2 microns on one side, and some pore much lower on the other side. The much lower is not a big problem. The much bigger is a problem because in that one you will see that liquid can penetrate, and so you kill some of the properties of the system. That's why some of you at this department and all around the world are working more and more to try to realize membranes that in reality have something similar in terms of configuration. All the pore, as much as possible, the same diameter. Such a way you can predict the condition, the parameter appropriate for running membrane distillation the right way. In this case, you can see here, you have, assuming this is strongly hydrophobic and porous, you have seawater, a salty solution on one side, liquid phase. What is happening here, just for the surface energy of this material, hydrophobic character, contact angle has to be the way to measure the hydrophobicity of a polymeric system is to measure the contact angle on the surface. If you drop water on your skin, you form a droplet. You can measure, you will see just the contact angle, and that's giving you an idea of how strong is the hydrophobic character. Assuming this is strongly hydrophobic, no liquid can penetrate, would be rejected. But at the interface between the liquid and the pore, assuming these pores are empty initially, you will have normal evaporation. The same as if I put a glass of water here on the floor, and now there's liquid. If I go out and I come after 1 day, the liquid is no more there, or the level is going down. What happened? Some molecules, the one at the interface, are just going in the empty space and trying to establish an equilibrium between liquid phase and gas phase at a certain temperature. And when the velocity of evaporation and the velocity of recondensation are equal, we are at a steady state. Here, what is happening is that at this interface, some molecules of the liquid phase will penetrate, will evaporate, and will go in this empty pore. For these molecules in gas phase, no hydrophobic characters can be defined. So this molecule will go across. If now I apply a small delta T, a driving force, few degrees centigrade, here can be 30 degrees, and here can be 28, just 2 degrees, 3 degree difference, these molecules can go across in vapor state. Only vapor is going across, no liquid. If there is any liquid, it's a problem, which is interesting because if we are telling this, we are now defining a new kind of selectivity in the sense that only volatile compounds can go across. In seawater, a lot of water, and there is salt, sodium chloride. Sodium chloride doesn't go in vapor phase, so selectivity here is 100%. It's not rejection that we define as a ratio between concentration upstream and downstream. Here is 100%. There is no molecules going from the liquid phase in the gas phase for what concerns electrolyte, salts, etc. Only the volatile can go. That means for seawater, 100% selectivity. If you have different system, water and alcohol, for example, alcohol is a volatile, or in wine, if you want to treat wine here, to concentrate, you must be careful, because some of the volatile, giving the aroma to your wine, etc., can go through. So in this case, you have to operate in a certain different way. Anyway, if this works, in principle, you can have molecules going across. You apply a small delta T, and you arrive on the other side. And here you can recondense your fresh water, because only water is going across. Engineers are working already on this system, and the way to realize this system can be different. You can have the condensation by different kind of configuration. You can have what we call a direct contact membrane distillation. So you can have just liquid fresh water on this side, so the molecules just go in the fresh water, or you can have, an aqueous solution here, or an air gap. That means just empty, and you can have a condenser plate at a certain distance, or you can have a vacuum, or you can have sweep gas. Each one of these different configuration is changing basically the boundary condition at the interface. It's changing what are concentration polarization phenomena of thermal polarization phenomena. This is a first case of a thermal membrane operation. This is not just a traditional membrane operation, it's a thermal one, it's a contactor. So here you have the same equation that characterizing any thermal system, and boundary condition for what concerns heat transfer are becoming very, very crucial. There will we don't have big problem with concentration polarization here. We don't have any convection, any pressure difference, so there's no convective flux to the feed side boundary layer, and so the traditional fouling is much less severe. But if we just have any motivation for creating temperature profile can kill the process. Temperature here is acting two different ways. One, I told you, a small difference in temperature, delta T, is necessary to move the molecules in a vapor phase from one side to the other. We can also realize this by different concentration, what is called today, this traditional, and also instead of calling membrane distillation, you call osmotic distillation, or what people are working in forward osmosis. You can put a draw solution, very high concentrate solution on this side, and you can extract by difference in the activity of the ions across. But normally you put a delta T. But temperature is very important for another reason, because changing the temperature of the feed, you facilitate evaporation. And if you remember, by exponential relationship, Clausius-Clapeyron equation is giving you an exponential dependence of the molecules going in the vapor phase, increasing temperature. So if you want to increase possibility of transmembrane flux, you have to increase temperature. If you go to 80 degrees here, you can compete with reverse osmosis in terms of flux. Otherwise, if you are working at room temperature, what we are trying to do today, to operate at very low temperature so you don't use too much energy, or you can use solar energy, which is impossible in traditional evaporation, you have less transmembrane flux than competitive technology, just because not too many molecules can go in vapor phase. And that's one of the problems to be studied, and the engineers is solved. For example, with membranes, if you have hollow fibers, you can have very much more pore available, and you can increase transmembrane flux. So that is the basic problem. Volatile compounds can evaporate at the interface of a microporous hydrophobic membrane, diffuse or convect across the membrane, and are condensed or removed on the opposite side. Okay? Which are the basic relationship and the driving force to the mass transfer. Traditional expression that we know for any membrane operation, the transmembrane flux of I is proportional to the difference in the partial pressures across the membranes, to delta P. And K is just the term of proportionality here, is just a function of temperature, pressure composition, and can also be the membrane structure because related to the hydrophobic or hydrophilic and morphology of the solution. Keep in mind that this expression normally is for, as always, for ideal. For non-ideal system, also here, your partial pressure has to be defined as function of it can be an ideal solution, or you have to introduce an activity coefficient to take care of the difference from ideal behavior of your system. And this kind of term is important because in membrane distillation and in other related systems as membrane crystallizers, normally you like to concentrate as much as possible your solution on the feed side. So you are quickly far away from any ideal behavior. And so one of the things that you have to do when you calculate driving force, and that means transmembrane flux, is to be sure about the value of your driving force, that's the partial pressure difference, which is very much related to the activity coefficient. You are normally far away from condition of ideality. And that is one of the things that you have to learn, and it's not easy to have a value of the activity coefficient of mixture at very high concentration. For example, at the concentration that we call a supersaturated solution, where we are approaching this heterogeneous nucleation, basically, starting crystallization. Quite complicated, not easy to find, and very often you have to try to measure by yourself. The relationship that I was mentioning before between the vapor pressure and the temperature, as you remember, is exponential, and is giving this kind of relationship, which is the typical Clausius-Clapeyron equation, where lambda here is the latent heat of evaporation, and the other parameters are familiar already to you, gas constant, etc., which means that one way to increase transmembrane flux is to operate not at 0 or 50 degree, but a little bit higher, 60, 70, and the dependence is not linear, but is exponential, and that will increase significantly your the possibility to have molecules across. But it's not this temperature that you have to create to move the molecules. The delta T of a very few, the delta T across the membrane can be few degree centigrade, 10 degrees centigrade. That is enough because the membranes are basically very porous. Most part of the volume is open. Porosity of this membrane can be 70, 80%, 85% are empty. So there is no mass resistance to the vapor going across this the system. If this is true, when you are going to operate in the real system, the transmembrane flux as function of the feed temperature will have this kind of behavior. Assuming that because just the vapor pressure has this kind of relationship, that's the same. The result you can obtain for water is exponential behavior as expected. Remember that for each kind of component, each kind of solvent that you can have a different behavior in terms of vapor pressure with temperature. That means that in principle, you can also try to separate, using the same methodology, different kind of solvents. You can separate water, in principle, from alcohol, eventually, or if there is a significant difference in the transmembrane, in the capability of the molecules to go in a vapor phase at a different temperature. Today, there are people trying to use membrane distillation not only for seawater desalination, which is a typical case, but to separate, I don't know, to remove chlorhydric acid, some acid, or ammonia from some industrial solution, where there are salts that you cannot, and they are not volatile at all, so they will stay, and you can remove some of the contaminants or some of the solvents as ammonia, as acid, the chlorhydric acid, typical case, from salts. That is still at research level, but big companies are just testing this kind of possibility because traditional methods don't work as expected. Also in this case, we have a problem of we have to understand mass transfer and heat transfer, because in this case we are warming up on one side of our membranes, which we are not doing all the system before, reverse osmosis, nanofiltration, ultrafiltration. We never spoke about delta T. The temperature on the feed side and on the permeate side was always assumed to be constant. If was not, is not normally not very important, and we have to consider also in that case what happened in terms of the different temperature. But we never discussed because it's not normally the case. Here, we have to consider both cases. Mass transfer, also here you can introduce an electrical analogy, assuming all the different resistance which are present, and the overall mass transfer coefficient in our system will be proportional, reverse, to the mass transfer coefficient on the boundary layer feed side, on the boundary layer permeate side, and in the membrane itself. So you have all these resistance, feed side, membrane, and distillate to be considered. If you are going to make now this analysis, and you will see which are the resistance which are present, for sure we have again, you can have a boundary layer resistance on both sides, on the feed and on distillate. You can have surface resistance inside the pore. You can have a Knudsen resistance, depending from the size of the pore, if the frequency of the collision between single molecules or the molecules and the wall of your pore are different. So you can have molecular resistance, Knudsen resistance, viscous resistance, just convective flow, etc. Normally in direct contact membrane distillation and in vacuum membrane distillation, these boundary layer resistance are considered basically negligible, not very significant. The same normally surface resistance are normally considered negligible, except You have special situation which can have adsorption or something. So that is a relatively easy system, and you can analyze eventually using in parallel or in a series the different resistance to the mass transfer that you can have across this system. When you will arrive, if you do this kind of analysis, the conclusion is that mass transfer resistance are basically not very important. They don't control the driving force across the system. It's totally different than in reverse osmosis, where the boundary layer, increasing concentration, you are decreasing the effective driving force, delta P minus delta pi. Delta pi is increasing, delta P minus delta pi is decreasing, and the flux was proportional to this term. So you just kill. Concentration polarization can kill completely the process. Not in this case. We were talking about Knudsen number. That means a system in which you can have this kind of situation with frequent collision with the wall of your pore more than the collision between the single pore. That is what we call Knudsen diffusion, and that's what we'll call molecular diffusion, where the predominance is collision between single molecules, and here predominance is the collision with the wall of the system. And depending from the relative size and the velocity of this ion, you can have expression for this Knudsen diffusion or molecular diffusion. In real life, what normally happens, that normally you don't have a very separate mechanism. Very often you can have overlapping of part of the Knudsen diffusion and molecular diffusion together. That is if you want to make an accurate analysis. But conclusion of this kind of analysis is that in principle, this effect, this kind of phenomena don't affect too much. There's no big resistance. These pores are big. There's no mass resistance to the vapor going across the membrane. Now, if you want to analyze the heat transfer, here we start to have troubles. And we can anticipate that the problem that we learn in reverse osmosis with concentration polarization are not present in membrane distillation because mass transfer is not a big problem. But we have exactly the same kind of problem we had in concentration polarization when we are considering the problem of temperature polarization, growing of temperature profile on the two faces of your membranes. So it's much easier in terms of concentration, much more complicated in terms of heat transfer. Keep in mind today, in membrane distillation, with the material we are using today, and with the configuration we are using, basically 50% of the energy that we supply to the system is lost. We are using energy not for moving the molecule, to evaporate molecules and to have the molecules going across, but we are using most part of 50% of the energy to warm up the polymer and creating eventually different temperature between the polymer on this side and this side, which we don't need. Nothing happened. So it's just loss of the energy. So people are working to try to solve this kind of problem, recovering most part of the heat you are supplying, inventing new membranes where thermal conductivity has to be very low. That means new materials with very low thermal conductivity, or traditional material filled with other material that are decreasing thermal conductivity, etc., etc. So this is another open field because today 50% of the energy basically is lost. What is happening for what concerns heat transfer? Here we have a relationship between simultaneous heat and mass transfer in terms of series and parallel resistance. We can do exactly the same analysis, but when you are going to analyze the total heat flux across your membranes, here is the system. You can have a problem on the heat transfer in the boundary layers on the feed side, on the boundary layer on the permeate side. Heat transfer coefficients can be, and they can be different, by the way, on permeate side, on the feed side, as in terms of mass transfer. But when you're going to see what happened in the membrane itself, you can have two different forms of heat transfer. Part is just related to the vaporization. We evaporate, and that's also we absorb energy. And this kind of heat is the one that is related to the vaporization and production of the molecule that has to go through. That is a useful one. But we have also conduction. Conduction is part of the energy we are supplying. It just goes through the solid material, not through the empty pore. And that is something that is lost because we don't have a flux of the chemicals that we want to move across. So that is one of the problems that we have, this conduction, and this conduction is not marginal. So that's one of the terms that we have to consider. That is the kind of phenomena that we have at the end. Remember, in concentration polarization, you are increasing the concentration at the interface. And so osmotic pressure is increasing, and so you are decreasing the driving force. Here, what is happening is that you are decreasing the temperature at the wall, and decreasing temperature at the wall, we evaporate less because temperature is lower. The driving force is less because delta T has to be applied for them moving across. So we have again a negative effect on the driving force and on the production of the molecule that can go across. So also in this case, you can define a temperature polarization coefficient, exactly in the same way that we have been defining a concentration polarization coefficient, but this term in temperature now have to be considered carefully, and that can be one of the terms that is going to kill your product. That's why the different kind of configuration we were showing before, direct contact, membrane distillation, vacuum, air gap, stripping, etc., each one of those, depending from the situation you have, has different performance related to this kind of phenomena that is introduced just for taking care of the boundary layer and the temperature profile that you can create. Much more important than in the other case. For what concerns the heat transfer, again, we have to, starting from the thermal conductivity of the polymer is important. If it's too high, it's a negative. We don't like to have high thermal conductivity. So we have to try to be as low as possible, and this is not, with the available material, is not, what we have is not really satisfactory. More than this, we have to consider, again, the two mechanisms I was mentioned before, the transfer of the latent heat of vaporization, which is associated with the mass flux, and the conduction through the membrane material and the vapor within membrane pore, which is related also to the membrane thickness. When you are looking to the heat transfer in the membrane phase, we have to rearrange a little bit traditional equation. Also in this case, as we discussed in previous case, you have to introduce the epsilon, which means the overall porosity of the membrane that normally is not present. So epsilon is the porosity, Ks is thermal conductivity of the solid membrane material, and Kg is thermal conductivity of the vapor within the membranes. Both terms has to be considered. The worst one is obviously the thermal conductivity of the solid membrane material, because that is just loss of energy. That is the one given this 50% I was mentioning before. Here's just some value if you have to make the calculation, and normally the Kg is 1 order of magnitude smaller than the Ks, so the heat loss by conduction to the membrane is reduced if we are increasing the porosity. That is, if you increase too much the porosity, however, what you are destroying mechanical properties. That is one of the areas where people are working. Today, the membrane that you buy commercially, they tell you that the overall porosity is the order of 60, sometimes 70. Very unusual. If you measure by yourself, this number is 45, 50. However, if you go in the lab and you discuss with your colleague that are working on new material you see that they can prepare today membranes with lab scale. You can have 80% porosity combined with a decent mechanical properties. And these are, if you do this on large scale, with significant contribution to solve this kind of problem. So already 80% porosity is quite interesting compared to what we have already on the market. That is just to show you how things are going depending from the material. The transmembrane flux as function of the thermal conductivity. Thermal conductivity is the driving force at this point in creating the condition for having the system running. is very dependent, and it depends also from the kind of material you are using. Polypropylene, PVDF, and polytetrafluoroethylene, the material we saw before in terms of thermal conductivity, are typical material for making membranes. Membranes, traditional for microfiltration. So people are using, we have been using until now this material that you can buy also on the market. They are not appropriate, however, for making what we want to do. It's just the only solution because nothing better exists. Here some of the numbers that characterize these membranes, and you can just utilize this number to predict, for example, the thermal efficiency of your system, depending from the size, diffusivity, etc. That is just one of the kind of work that you can have to do if you want to predict the performance of your membrane installation. That is basically what we are telling, is that the possibility to realize the system is related to the possibility to control these interfacial phenomena, and I was mentioning that each one of the different configuration has a little bit different properties. For example, in principle, direct contact and vacuum are the one where the boundary layers can be better controlled and the effect in terms of the thermal polarization are smaller. This typical case, this is the most traditional one, also because the most simple one. You have seawater on one side, and then in most part of the plant running around the world, normally you have this kind of configuration today, or the vacuum. You have just seawater on one side and just fresh water. You start with fresh water on the other side. So what is happening that fresh water is going across. You have evaporation on one side, in vapor phase going across, and you dissolve the water molecules in the distillate side. So just produce fresh water just using the delta T. That's what is important, however, that here you can operate at any temperature. You can evaporate water also at 20 degrees centigrade. Few molecules, but you can do. And if this number of pores are billions and billions, if you have nice membrane surface with a nice distribution of pore, the fact that there is very few molecules for single pore is just can be facilitated by the fact that you have billions of pores. If you multiply each pore for the number of molecules, you have significant transmembrane flux. Still not competing at low temperature with reverse osmosis, for example, but the big benefit, that's why all the Middle East is working today with membrane distillation, that you can have this kind of distillation with using solar energy. That means you can operate with system that temperature can be 30, 35, 40 degrees. You don't have to arrive to boiling your water, don't have to arrive 100, 120. In Saudi Arabia, we mentioned already, they are burning today 15 million barrels of oil to produce the water they need. And tomorrow these 15 millions can become 30 million, 50 millions. And that is a big cost. If they can use solar energy, they can sell the 30 million barrels, and you know how much does it cost today, the oil, and there's a lot of money. So that's why they are looking more and more to use membrane distillation instead than MSF, etc., because they can operate at much just using solar energy. In fact, all these plants are basically solar energy and membrane distillation today. In Europe, we have different projects of this kind. We've been involved in some of them, and today, if you go in Tunisia, in the middle of the desert, you find already some factory where solar energy and membrane distillation produced by this Fraunhofer Institute on Solar Energy are already running. That's what's part of a project called Medidas, and that was the way to realize. And these are already operating on small scale, but they can already operate. So that is the kind of situation we are talking about. Now, in this situation, if you just measure the heat lost, depending from the different delta T, as a function of the transmembrane flux, you will see that, that this effect is quite significant, and increasing the transmembrane flux, the heat loss is increasing. That's why one thing you have to do if you want to compete, if there's no other reason for introducing MD, is to make this kind of analysis and realize how much is the heat loss in the system. Because I was mentioning heat loss, and that's the heat loss in terms of conduction. The one that we were discussing is the origin of the problem. If you know material, with different thermal conductivity, one we have been considering and people are considering, this kind of plots can be much more interesting and useful. And that I was telling basically is not the number here, but I can tell you this is basically about 50% of the production. Different other parameters to be considered exist and can change the overall performance. Here, for example, the transmembrane flux as function of the deltas different in temperature across your membranes. Keep in mind that exactly the same kind of phenomena that we had talking about osmotic phenomena can take place also here. Here you can plot transmembrane flux as function of delta T. We were, in osmotic phenomena, we were plotting transmembrane flux as function of delta P, different in the static pressure. And we realized that there was one value of delta P that if it was lower than delta pi, we have reverse flux. Instead of producing water, you were absorbing water. Same phenomena can be here. If you have a transmembrane delta T, which is not sufficient to create the transmembrane flux, you can have a negative flux instead of positive. And this can happen as a function of what I was mentioning before, for changing of the activity of the component of your solution. Because you can be far away from ideal character, and so your prediction were wrong. So the net flux can inverse the direction if the delta T is not sufficient to compensate the reduction of activity on the retention side. So you have to take care of this, otherwise you can have this phenomenon is less severe than in reverse osmosis, but exactly the same kind of phenomena. It's less, not linear, by the way, as we had in delta P, because linearity was characteristic of the Van 't Hoff equation, but here you see that we don't know that it's not linear, but it's the same kind of phenomenon. Another point that is very important is that delta T can be created in a different way. You can create a delta T warming up on one side and keep it constant on the other one, or vice versa on the permeate side. Vice versa, you can keep constant the temperature on the feed side and decrease temperature on the permeate side. And this does not give you the same results because this boundary layer phenomena can be different, and the overall heat transfer can be different. So when you have just making your plot, you only have to tell how you have been creating the delta T. And experimentally, you can have different delta T depending on if you are warming up on one side and cooling down, or vice versa, for the boundary condition that we were just showing before. That's a typical case that you can have. Here you can see also how the variation of the transmembrane flux is a function of the feed and distillate flow rate. Again, nothing changed the membranes, but is it boundary layer phenomena, interfacial phenomena, and that can be quite significant. You can have different flux depending from the flow rate that you are applying to the system, from the Reynolds number, that means the velocity in which you are just moving your solution at the interface. So again, all these plots are telling you which are the parameters on which we have to operate, not in the membrane itself, but to control the boundary condition, which are quite effective as we learned already in reverse osmosis. That is again something that is giving you the thermal efficiency that can increase significantly with a high temperature. Increasing temperature can increase thermal efficiency. And here is the same that feed flow velocity, the flux, transmembrane flux, is increasing significantly when you are increasing flow velocity and feed temperature. Again, these parameters are giving you how we can improve the performance of this kind of operation. One difference with all the process we have been discussing before, and that means is a difference in producing your membranes. Normally, no, we are assuming that the transmembrane flux, if you increase membrane thickness, is always going down. And it's going down also in this case, also membrane distillation. But transmembrane flux is not the only important parameter here if you want to evaluate final cost and energy consumption, because the thermal efficiency we have been discussing before is quite important. We are losing 50% in energy in warming up the polymer with the material we have today. which means that the thickness is becoming quite important now. Because depending the thickness, increasing the thickness, you decrease transmembrane flux, but you are increasing the efficiency in terms of energy consumption. Because if you increase the thickness of your membranes, you are decreasing the thermal loss across the membrane itself. So at the end, here these two plots are going through a minimum. So you have to optimize in terms of thickness or in terms of thermal efficiency that is going up. So your colleagues, students, are working in just to try to optimize thermal efficiency in terms of flux. Both of them are important for the final cost, but they have totally different behavior, and in some case, you have to one of the reasons for which the existing membranes today, already commercial, produced for microfiltration, are not appropriate for membrane distillation, is that for membrane distillation, you can increase the thickness and not decrease it. Sometimes they are too thin for membrane distillation. You can produce the same but thicker than the one because you can increase thermal efficiency. Also if you lose in transmembrane flux. Okay? Thicker membrane, the thermal efficiency increases gradually as the membrane thickness is going to increase. Which are basically the membranes we are using today for this kind of operation. This is a total open field, as I was mentioning. If you go on the 10th floor, some of your colleagues are working for producing better membranes for one side. When they make hydrophilic, is for membrane for microfiltration, ultrafiltration. When you are looking for hydrophobic material, be sure, also if they don't tell you, but they are working for membrane distillation. You can find the plants for measuring membrane distillation. You will see plants where temperature, what you measure is temperature, is not pressure, it's not the traditional concentration, it's just temperature on one side, on the other one, because they are looking for this. This membrane can be symmetric or asymmetric. We don't have any big problem in this case, also because, as I was mentioning, traditional fouling is less severe. You can have situations in which big fouling, if you are working in nanofiltration, ultrafiltration, because you have convective flux to the membrane surface, you are pushing the solution to the membrane surface, you can accumulate solutes, and you create gel layer, double layer, etc. Here you don't have this convective flux. It's only you evaporate. And so that's minimize traditional fouling. And from this point of view, asymmetric is not really necessary because we are introducing asymmetric material also for avoiding any penetration, etc. No big trouble. Symmetric or asymmetric. Thickness, normally from 20, 100 nanometers. This is also important because it's related to the thermal conductivity. So this number can change depending for what we have just mentioned, that the thermal conductivity is also a function of the thickness. Pore size, we will understand why, has to be in relatively narrow range. 0.1 or 1 micron, don't read the millimeter. Oh, that is 0.2, 0.3, sometimes is also better. Don't read the millimeter, this is microns. Membrane material, hydrophobic. Sometimes can be hydrophobic, hydrophilic. You can make a coating, some hydrophilic, to avoid some loss of hydrophobic character, to protect the membrane for interaction of some components, surfactants, alcohol. They must be resistant to alcohol and surfactants, in fact, because alcohol and surfactants are making hydrophobic material hydrophilic. Porosity, as much as possible, 70, 80. Most parts of the membranes today available are 45, 50 in real life. Also, if they tell more, check by yourself. It's quite difficult to have much higher. Why this? This material has to be strongly hydrophobic. We are discussing all in water. If we are going to discuss in organic solvents, this will be just opposite story. But in water, materials to be hydrophobic, to be sure that no liquid is going inside. We don't want to have liquid. If you have liquid, selectivity is going down, because with the liquid, solvent and solutes will penetrate. So basically you have a solution and you just don't have any fresh water on the other side. So what you have to realize for measuring the hydrophobic properties is to have a contact angle, this angle here, that is of the order of higher than 1995. The you define normally hydrophilic material when it's lower than 90, 80, 70, 20, and you define hydrophobic when it's more than 90, 95, best 100, 120, super hydrophobic sometimes is 150, 180. Be careful that hydrophobic character sometimes is not a permanent status. If you induce some hydrophobic character by, for example, plasma deposition, by attaching some fluoropolymers, which are typical hydrophobic material, you have always to check lifetime of this hydrophobic character, because you can have what's called a recoil phenomena. You can have a nice hydrophobic character for 5 hours, 5 days, 1 month, but slowly these hydrophobic characters disappear. These membranes has to work as the reverse osmosis membrane. 5 years, 10 years if possible, not short term. So when you are talking about how to increase hydrophobic character, we must be sure that it's not only for writing a publication, but for solving a problem. That means very long term, very long stability, which is not so easy. For understanding what is happening, this is the angle, the contact angle that we have to measure. We want to have these droplets basically not absorbed in the material, but totally rejected. And this angle here, this one is not good enough. That is more hydrophilic. This means the liquid is dispersed and absorbed in the material down. Hydrophobic means that we have a nice droplets on the membrane surface here. The equation that has to be considered is what is called this Young equation, where you have the surface tension for liquid vapor multiplied for the cosine theta, the contact angle that we were just showing before, and this normally is equal to the difference between surface energy of the polymer minus the solid liquid surface tension. So these are the parameters that we have to consider, and depending from the different liquids that we have available, you can have very different value of this LV, of this basically surface tension for liquid vapor. They can go from 73 to 20 to 40, etc., depending what you are measuring. That's why I told you have to define in which system you are working. The equation that we wrote before, the Young equation, is normally valid for flat sheet, no smooth surface. We don't have normally a smooth surface. We have surface on the membranes where we have normally a certain level of roughness and a certain level of porosity. So the porosity is changing this property of your surface. So you have to introduce some factor to correct this contact angle for this different non-ideal surface. Basically, you have to introduce this, again, porosity and pore tortuosity. And they are going in this in the new cosine contact angle, for example, has been measured for Teflon. That was one of the first membrane utilized for this application. And you can write again a correct expression for the contact angle. It's a little bit complicated, but it's basically related to the porosity and the tortuosity of your membrane. Why this is very important? It's quite important because there is another equation that you have to remember. Everybody working in membrane contactors in general, and the membrane distillation particularly, has to be very familiar with the Laplace equation. Laplace equation is telling you that when I'm talking the system is hydrophobic, no liquid will penetrate, which is the relationship between the possibility to penetrate or not penetrate. That is the parameter, this L, what we call liquid penetration pressure. For any material with a certain level of hydrophobic characters, the possibility that the liquid penetrates or not is related for sure to the contact angle, and that is for the theta here. But is also related, you see a denominator, to the size of the pore. If the pore is too big, this LP, that means this difference between the penetration pressure, is becoming very, very small, as shown here. That means any few millimeter of water pressure will move liquid in, and that is decreasing the possibility to utilize in membrane distillation. So this possibility to have a good only vapor going across is related for sure to the cosine theta and to the gamma, but is also related to the size of the pore. And as I was mentioning before, that is typical relationship. You can see here the vapor entry pressure as function of the size of the pore. If the size of the pore is 1 or 2 microns, these values are becoming very, very small. So just because, for example, you have a difference in cross-flow velocity on one side of your membranes and on the other one, you are creating a pressure drop across your membranes, and that can induce liquid penetration if the pore are too big. If the pore are, the entry pressure will be much higher when the pore are smaller. In this case, you can operate at 1 atmosphere, 3 atmosphere, 5 atmosphere, 10 atmosphere, nothing will go through. And these membranes are the right one. Obviously, you have to also here to find a compromise. Normally, that's why we were mentioning before, the ideal value is around 0.1, 0.2, 0.3. This is the range in which we like to have our membranes porosity. Because in this case, we have order of magnitude of the LEP of the order of 5, 6, 7 atmosphere, and so there is no problem to have any liquid penetration if you don't apply 7 atmosphere. But normally it does not happen that you create 7 atmosphere by pressure drop, etc. Okay? So that is important. On the other side, this is big trouble. Today, in some country, Singapore, for example, or all the electronic industry is already using membrane distillation. They want to use more and more membrane distillation for producing ultra pure water. In the electronic industry, I was mentioning already before, ultra pure water is very important, otherwise, if you don't want to go out of the market. This system is ideal because selectivity is 100%. No salt is going through. Also, you can extract oxygen also using the same technology, by the way. However, if the membrane porosity is not very sharp, if you don't have a very narrow pore size distribution, as we expect and as we show ideally in our scheme of the membranes, you can have most parts of the porosity around 0.2, 0.3, but still few pore at 3, 4, 5 microns. And through this pore, we can have a liquid penetration, so you can still operate in desalination, but you don't operate for sure in ultra pure water production or for injection in the body, because some salts can still go if there is also 1, 2, 3, 4 pores, big size. That's why you have to work today, you will find literature people, as ourselves, trying to produce membranes with a very, very narrow pore size distribution, as much as possible around 0.1, 0.2, 0.3, where this water entry pressure is relatively quite high, so we don't have a big problem. And if you go again on the 10th floor, some of your colleagues, for example, when you will study about how to make membranes, you will learn, for example, all this material we are using, you can use different way of phase inversion. One is a NIPS, that means a room temperature phase inversion, or TIPS, thermal phase inversion. If you want to produce very narrow pore size distribution, you have to produce TIPS. TIPS is giving you very narrow. That's why you use more energy. It's a little bit more tricky. Working high temperature is always a problem, but you can solve. And that's why people are working here at TIPS, because they want to produce membranes with a very narrow pore size distribution around this number to be utilized in this system and not having this problem down here. So that is one of the important aspects of the situation, to avoid as much as possible the big pore. This equation is one of the equations that you have to consider with attention, because it's always present in our process, not only membrane distillation. The same story will be membrane crystallization, membrane condenser, etc., etc. Membranes of this kind already exist. Initially, they were produced not for membrane distillation, but for the extraction of oxygen. This term here, this is the first industrial application. But these membranes were done to extract oxygen from water, ultra pure water in electronic industry, where not only salts, but also oxygen has to be avoided today with the standard of your mobile, etc., of our chips. Also oxygen has to be out. This system can be utilized to extract also oxygen to molecular level. No oxygen will be there, just using the same kind of logic. Basically, that you see here, per side 0.2, 0.03, 0.02, just in the range I was mentioning. And the material is again polypropylene or PVDF. And you can have a flash sheet or you can have hollow fibers, exactly as in the other kind of problem. So this is the structure of the material. As you can see, most of them are just, except polypropylene, are fluorinated polymers, as a PVDF or Teflon, because fluorine is a typical atoms giving some hydrophobic character. It's quite interesting. They have interesting chemical resistance, hydrophobic character, stable at high temperature also. What is interesting today, new materials are becoming popular, and this new material just popular in membrane field just for this kind of application, not for reverse osmosis or ultrafiltration. So some of you is already familiar with HYFLON, with a very, very chemical resistant, very expensive, but very hydrophobic and stable. This will not change in few hours. Very strong hydrophobicity. You can make membranes 120, 130 in contact angle, and will stay forever. It's quite expensive. Better than PVDF is the most traditional membrane, but today another polymer is becoming of interest. It's called ALAR. That is the ethylene chlorotrifluoroethylene copolymer, and it's the typical structure. And the reason for which ALAR is becoming of interest is because it's much better than PVDF in terms of not hydrophilicity, etc., but hydrophobic character. So this one is becoming, it's on the market. People are starting to utilize and to study, including at Anyang University, for the possibility to have a better membrane for membrane distillation, not just for traditional application. And quite interesting, and also at different significant interesting cost. That is the difference between the two different structures. And you can see here, you can make nice, interesting membranes with relatively nice pore side distribution. What you can do more is to make composite membranes in this work, because HYFLON is very expensive polymer. HYFLON, this kind of stuff, this is basically the same cost of Teflon, the most expensive Teflon produced from DuPont. This HYFLON is produced in Europe, and the traditional Teflon is produced in the States. This costs you about $14 per gram. So making membranes on large scale with this cost is not so easy. So what you can try to do is to make a composite membrane. You can use the polypropylene or PVDF as a kind of a microporous membrane, but you can increase hydrophobic character by making a very thin deposit of HYFLON on the membrane surface. And that's something that, for example, we have been working on. If you do this, you have quite interesting results. You can see the porosity can be relatively high. You can go with porosity about 70%, 80%. And what is also interesting that the mechanical properties are the pore side distribution is the other parameter to measure. As you can see here, very narrow, around a certain number. That is, this is a little bit to be known, but 0.2 here or 2 microns, etc. And what is also interesting that the mechanical properties are also quite interesting when you make these coatings, because HYFLON is a very interesting mechanical property in general. So this is one way of doing, is to try to integrate HYFLON with PVDF for having material that can be of interest for this kind of specific application. Contact angle you can see here from 26 to under 40. This is a super hydrophobic character if you can do this. But what is important, not only have this number for a long time, because if this kind of phenomena sometimes are short. They just appear, they stay for some time, but slowly they are not at equilibrium, slowly they disappear. So you have to find material that will give this value for years or for long time compared to the kind of application that are necessary today. However, today people are looking also to have different kind of material and different kind of morphology. I show you that what can be done here. There's some work that also we have been doing. This is the polyether ketone with Cardo group. We have been mentioning already last time. And the interesting structure, this is the lactone group up there, giving this capability to this polyether ether ketone to become soluble in the solvent. Normally this is very, very not soluble. So if you want to make membranes, you don't know how to do it. So because you have only to melt, to go high temperature, you destroy the polymer. The Chinese introduced this lactone group, and this one is basically soluble in the normal solvent. So you can utilize. What's more interesting, that you can utilize and you can introduce some modification that somebody will do also on the 10th floor in the phase inversion, controlling the concentration of the gas phase in a closed chamber, and you can have this kind of final structure. It's interesting not because it looks nice, but because you can see that the pore size of each one of these pores is equal to the other one. So very, very narrow pore size distribution. These things is obtained basically if you are able to condense, when you have the condensation of this gas phase, droplets of water at a certain temperature, vapor pressure, they condense in the polymeric surface during the phase inversion. And these droplets we are not very aware initially, they are all equal, one to the other. Just the condition that you create give you condensation for droplets all equal, which means that each one of those was a water droplet. After you just remove the water, and what is left is just all the pore equal because they were formed due to the kind of template, and it was the droplets condensation. Quite interesting because now if you change, if this is water, is one size at a certain temperature. But now if you put water with alcohol or water acetone, you change it, the droplet size is different. So you can have different kind, the same morphology, all equal, but different kind of size, changing the composition of this phase inversion in control atmosphere, basically. Quite interesting. High porosity, surface porosity 85%, quite useful. However, the best you can do on this today is a small piece of this kind of membrane. If you want to scale up and doing this one, roll to roll as is necessary, forget for the moment. But slowly, when the people will start to invest, and in this area, this can be produced on large scale, and that will be one possible solution to the problem we are discussing. Membrane distillation has a lot of possible application, much more than expected. And I told you it's becoming more and more popular. Plants are already in operation, not large plants, not producing millions of cubic meters of fresh water, but 100 cubic meters per day. They already exist, particularly in the Middle East, in Singapore, in China now, and maybe soon also probably in Korea. And so the desalination and pure water production from seawater or brackish water. Keep in mind some application that are not, nuclear industry. Nothing is going in vapor phase. So if you have, for example, the problem that was in Japan, or radioactive isotopes, very difficult to treat with normal membranes, because radioactivity, energy, it can just attack the polymer, by the way. These are fluoropolymers, very resistant. But second, no ions is going vapor phase. So cesium or cobalt, etc., they can 100% remove from the water if you utilize this kind of technology. Unfortunately, this has to be done on large scale for the problem they had. But this will be the way to, for the next event, to avoid the problems. This kind of methodology can remove completely all the ions, 100%, no one will go into this thing. And that's why it's already suggested concentration of radioactive solution and wastewater treatment for pure water production or clean water production. Textiles had a lot of possible application, and I was mentioning already that we saw in the introduction lectures that if you go today, country as Korea, and you see how Korean researcher will spend $70 million in the next 4 years, membrane distillation is one of the issues on which they are putting the money in desalination, brackish water, seawater, because that's one of the way of doing. And that is a typical example of what is going to happen in the next few years. And the same in different other fields. Just to remember what I was mentioning at the beginning, and just to clarify that there's nothing new. It's just learning from nature. Because the problem of the evaporation and condensation, that means distillation, is very long. It's natural hydrological cycle. all around the world, from long, long time back, we have evaporation, cloud formation, condensation, changing temperature, going back as a liquid water, and again starting cycle again. People realized already long time ago, you can find evidence written in Arabic. That's one of the areas where Arabic already started in the 70s, just a few hundred years after Christ was born. They started to use this kind of phenomena by emphasizing the evaporation by thermal supplying some thermal energy, making the alambicus, etc., and that was the idea. Engineering has been working a lot, and they created distillation column, which are spread all around. All of you probably at high school or university have been learning about distillation in this form, etc. But if you analyze this kind of system on the basis of process intensification, all the parameters are not respected. If you put this PI index, no one is respected in terms of everything: footprint, energy consumption, size, flexibility. If you want to change, if you build up a plant for 50 million cubic meter per year, and you want to go to 55, the only thing to do is take the plant, put in the garbage, and build another one. You cannot change the size of the plant, etc. That is the way in which today you can redesign the same kind of phenomena, same basic equation, nothing changed in terms of basic approach, instead in this way, exactly as nature has been doing, because nature is already using in our body, we're using this interfacial hydrophobic materials, where on one side you can just evaporate across the pore, on the other side you can condense what the pore was moving in vapor phase. That means very selective, etc. Which are the real benefits and where we are competing? Because everything I told you can be summarized, for example, in this plot. This plot is giving you the transmembrane flux as function of the feed concentration. And what you can see here, that if we are working with a reverse osmosis, when the concentration is increasing, and that can increase if you are using higher concentration of salt, but for concentration polarization, transmembrane flux is going to zero quickly. Already at about 85 grams per liter, that means less than 1 molar. No, this is not a little bit more than 1 molar. The molarity of sodium chloride is 58. So if you have 1 mole per liter, when you are around here, 60, you have basically 1 mole per liter. 85 will be 1.5, 1.6 mole per liter. Flux is zero if you don't increase significantly the pressure. You have to work with a feed pressure of 10, 20, 30, 50 atmosphere if you want to overcome this situation. If you are doing the same exercise in membrane distillation, you can, in the transmembrane flux, what we are looking for, can go 100 grams per liter, can go to 300 grams per liter, 400 grams per liter. Basically, it's still the same. Small decay because activity coefficients have to be considered, so you have deviation from ideal character, etc., etc. But an increase in temperature, you can increase significantly the transmembrane flux, and constant with the concentration. So that's the reason for which, if you want to improve recovery factor of in distillation system, today the best we can have using reverse osmosis, forget traditional distillation, where the recovery factor is about 20%, now 15, 20%, 30% with a lot of complicated engineering. In reverse osmosis, we can already approach basically about 50%. In some cases, if you introduce nanofiltration upstream, that means reducing bivalent, you can increase a little bit recovery factor. Remember, we define recovery factor when we discuss about pressure driving, the amount of permeate compared to the total supply of your solution. Recovery factor here can be theoretically 100%. We are working recovery factor with 95%, 93% already. So increasing more double than what you can have with traditional system. And that's quite interesting. More than this, rejection is 100% basically. The selectivity is exactly the same than what you expect. remember what I was mentioning, that this can be done at 20 degrees centigrade. You can increase the surface available, number of the pore, eventually, but you don't have to warm up too much. You can work at 25 degrees. Evaporation is taking place at any temperature. And the transmembrane flux will increase with the surface available. These plants are the one I was mentioning before in Tunisia. That's the one from one of our European projects, where you have solar energy. This is in a remote area in the desert inside Tunisia, and in some factory, and you can have just solar energy and these 3 modules with flash heat, in this case module, and you just produce fresh water, much better than what is necessary. Here you have to re-add some salts, otherwise but this can be a way. That's one of the things that people will do probably for security sometimes, also on ships, because this system is relatively very, very simple. And in principle, you don't have a big engine and you don't have also to work too much in terms of controlling concentration, polarization, etc., which are the real trouble. The only point is the material for your membranes for the problem of thermal conductivity we were discussing before. Also, this is under study, and people are trying to solve the problem in a different way. That is a system in which you can just have a heat recovery system. All the excess of energy you can try to recover again, as we do with pressure in reverse osmosis. In reverse osmosis, you are putting a turbine or a pressure exchanger. Here you have to use a heat recovery system that can be external to the system or just internal one. These people from this Fraunhofer Institute, they also invented the system in which they introduce another membranes inside the spiral wound system, where this excess of heat that we are forming can be condensed and reutilized inside the system itself. So you can have just a system where you can recover external or also internally. Or there are engineers that are just trying to learn from traditional multi-flash, for example, but instead of making a column of different evaporator and condenser, they try to combine this multi-effect technology in multi-effect membrane distillation technology, and you can have a series of cooling and warming, but with the membrane itself. So very open field where everybody still can have ideas and supply new way of doing, particularly for the problem of reducing the energy consumption and not losing this 50% of the heat. Trying to recover it, as you can do in this way, or trying to use new material much better than the other one. In some prediction in costs, it's interesting that recently chemical engineers in the United States, for example, they are considering this system with direct contact membrane distillation with hollow fiber heat exchanger, because they're basically a heat exchanger, and they come out with numbers giving you about this direct contact membrane distillation, less than 0.60 cubic meter, cents of a dollar per cubic meter, which is basically better, it's not than reverse osmosis, some situation. I don't think that this number in real life will become useful. I don't think that the reverse osmosis will disappear. Reverse osmosis will also be the most interesting process. However, reverse osmosis has some limits. Recovery factor 50%, because the concentration polarization phenomena cannot be totally avoided. That's why the real solution will not be trying to cancel reverse osmosis, but try to integrate reverse osmosis and membrane distillation. You can use the benefits of reverse osmosis in terms of much lower energy consumption than thermal system, up to a recovery factor of 50%. At this stage, when you cannot operate anymore reverse osmosis, you can introduce membrane distillation on the retentate or the concentrate of RO using MD, where MD can still work nicely with no problem at all. So if you're able to integrate the two systems, RO and MD, one membrane system and one thermal system, because this is a thermal system, you can arrive up in, for sure theoretically, but probably also very experimentally, very quickly, to operation at 95, 97%. And if you do this, if you arrive to this value, you will have a lot of benefits. And you will be able to realize what we were discussing the other time in terms of possibility to combine not only freshwater production, but also to introduce a new strategy, because when you have a 95% recovery factor, you can have a lot of concentrate available, a lot of salts. And these salts, we will see next time, will be the origin of another unit operation, very interesting and appropriate more than membrane distillation, which is membrane crystallizers. To close this one, remember, this is again one of our students, he's coming from Oman. In Oman, one of the first plants of this kind is now installed in the desert of Oman. I don't know if you've never been to Oman. If you have any time, go to Oman. Very interesting country, very beautiful. But if you just analyze now the cost of water production, as we were mentioning before, that the water cost as function of temperature gradient in the system, you can see here, just because of what we were mentioning, there's a problem of membrane cost and there's a problem of heating cost. For sure, if you are giving more energy, if you are warming up, you increase, remember, this energy efficiency. However, and you are decreasing membrane cost, because if you are increasing transmembrane flux, you can, for the same productivity, you can reduce this membrane surface necessary. But these two effects are competing, and that means that if you want really to do correctly your analysis of the cost, you have to consider both of them. You have to consider the cost of the membranes. You save membranes by increasing temperature, and you have to consider the cost of the energy. Assuming the same thickness. Here, students are still working to introduce also the effect of the thickness, which we learned before, can affect the cost of the efficiency of the energy. But you go through a minimum. And when there is a minimum, it's always a little bit complicated, because you have to define all the parameters and find which is the temperature gradient optimal for your to have a decent water cost. Quite interesting, but these things already are becoming more and more easy to understand. This cost here is a little bit higher than the one that Sirkar was showing, 0.6. We were working on the order of about $1 per cubic meter, but quite you can learn about. Selectivity, we were mentioning 100%. Sometimes when you measure, it's not 100%. Still quite good. 99.7, 99.8 is not 99.999. Why? We learn now. It's not because membranes, the one membrane utilized here, commercial membranes, they don't have a sharp pore size distribution. The 100% is only if all the pores are around 0.1, 0.2. All these membranes are much far away for having this kind of result. That's why you have this small deviation from the value expected, but still quite competitive with most part of the real membrane. That also when in RO, also when they tell you 99.5, when you go to measure, it's 98.5 or 99.1. These are all 99.7, 8, etc. So quite interesting as a value. All this story here is very much related to another process, which we call membrane crystallizers. And now you understand already the membrane crystallizers is nothing more than membrane distillation extrapolated to the extreme case. Because if you are able to concentrate and concentrate and concentrate, still having a constant transmembrane flux, and you know about crystallization, you are able to create a situation in which you produce what is called a supersaturated solution, a solution approaching saturation. This is step number one for what is called heterogeneous nucleation for the crystallization of salts. And that's a critical step for any crystallization process. So with this kind of system, we can realize, in principle, a continuous crystallization. And as we will discuss next time, exactly the same logic, same technology, but you have to be able to avoid to block the system, because if you form a huge amount of crystals on the membrane surface here, nothing will go through. So if you are able to operate in this way, where you just you create a supersaturated solution on the membrane surface, and in the meantime, you remove continuously the solid crystal that you form, when they start to be formed, to avoid to plug in everything, that is what we call a membrane crystallizers. And this is, again, becoming one of quite interesting because initially it seemed that this system is only to evaporate. It helps you to evaporate because we evaporate. That is typical crystallization by evaporation. We arrive to saturation and you precipitate your crystals. It's much more than this. Because when you start to do this, you learn that the properties of your polymers, the morphology of the surface, the energy, the surface energy, etc., is inducing a lot of phenomena. For example, is reducing activation energy of the nucleation. So the crystal can grow much faster than normal. More than this, you can realize some certain level of concentration in a specific part of your system that induce specific form of crystallization, for example, protein, that was unexpected, and you understand why these things happen. But the most important aspect is that doing this, you can add to the normal crystallizer some more benefits. For example, using this concept, you can crystallize polymorph. You know that most part of the chemicals, biochemicals, but also salts, exist in different final crystal habits. You can have magnesium sulfate, can be magnesium sulfate with 5 molecules of water, 7 molecules, 2. One of those is, for example, I think 7 molecules, is called epsomite. It's the most interesting and expensive quality of magnesium sulfate. Now, when you work in this way, where you can control a lot of parameters in a very interesting way, all the interface of concentration, etc., you can produce not magnesium sulfate. You produce epsomite. And epsomite, people pay you $20, $15 per kilo. So forget about the water, and you just you sell epsomite, and that is the real benefits. And that is quite interesting because all these new unit operation are improving the performance of the traditional one they are competing with. So we will start to discuss about membrane crystallizer next time. Thank you.